So a chessboard is well known by all of us as an 8x8 square grid, but most people get it wrong when you ask how many squares it has, as they say 64, which isn't entirely correct, just to jump to conclusions. In this video, I'll explain the real answer and jump into some cool maths I encountered in my research. So most people's first mistake is assuming that the only squares that count are the small ones, 1 by 1, but the question gets far more interesting when we count all the squares, including 2 by 2 squares, 3 by 3, and all the way up to the single 8 by 8 square. Now before we waste our time trying to count all the squares on an 8 by 8, let's build some intuition on a smaller grid. Here's a 4 by 4 grid, much easier to count up. So here are all the 1 by 1 squares. There are 16. If we count the 2 by 2s, there are 9, and for the 3s, there are 4. And then finally, the last 4 by 4 square, making a total of 30. So is there a pattern with 16, 9, 4, and 1? I bet we all already see it. They are square numbers. But why do they appear here? Let's take a closer look. So for 1 by 1, it's quite obvious. But let's look at 2 by 2. If we look at the top left corner of the subsquares, you'll notice that they form a 3 by 3 square within the 4 by 4. As they need a 1 square buffer from the sides since they are bigger. This extends to 3 by 3 squares whose corners form a 2 by 2 square, as they need a 2 square buffer from the sides, and then sort of trivially 4 by 4, which has 1 corner since you can only fit 1 inside. Now let's use this on our 8 by 8. So first we have the known 64 1 by 1s, but if our assumption is correct, there are 49 2 by 2s, and if we extend this up to 8 by 8s, we get 64 plus 49 plus 36 plus 25 plus 16 plus 9 plus 4 plus 1, which gives us 204 total squares. Now that's all well and good knowing it for a chessboard that's only 8 by 8, but what if we have an even bigger board, let's say 100 by 100? No one wants to sum up all 100 terms, so what if instead of summing them up, we make a formula, ideally a polynomial, where we can just throw in x and be done? First, let's figure out the largest term of our polynomial. It's not going to be constant or linear since we are summing up squares, and it's not a quadratic since it grows by a quadratic amount every time x increases. So that leaves us with a cubic. So let's set up a cubic equation. ax cubed plus bx squared plus cx plus d equals our sum of n squares. Since we have 4 variables, we'll need 4 equations. We will use x equals 0. We have a 0 by 0 square, so 0 squares. For x equals 1, we get 1. And then for x equals 2 and x equals 3, we use our old formula to get 5 and 14. Now, if we sub these in, we get these 4 equations. 0a plus 0b plus 0c plus d equals 0, a plus b plus c plus d equals 1, 8a plus 4b plus 2c plus d equals 5, and 27a plus 9b plus 3c plus d equals 14. Now our first equation tells us d equals 0, so we can remove it from the rest of the equations. We can use the second equation to show c equals 1 minus a minus b. If we sub this value into our next equation, we get 8a plus 4b plus 2 minus 2a minus 2b equals 5, which simplifies to 6a plus 2b equals 3, which tells us b equals 3 halves minus 3a, and c equals 2a minus a half. We then use the final equation to show 27a plus 27 over 2 minus 27a plus 6a minus 3 over 2 equals 14, which gives us 6a plus 12 equals 14, so 6a equals 2, which means a equals 1/3, b equals a half, c equals a sixth, and d still equals 0, giving us our equation 1/3 x cubed plus 1/2 x squared plus 1/6 x to x is our sum of x squares. Now, if we check this with a graphing calculator, you'll see this is bang on for all of them, but this only leaves one question. What happens if we go one dimension up or down from 2D? We can use the same logic to reach the same conclusions for both how many lines are in a line for one dimension, which is the sum of integers, and how many cubes are in a cube for 3 dimensions, which is the sum of cubes. Their formulas are a half x squared plus a half x, and 1/4 x to the 4 plus a half x cubed plus a quarter x squared. This logic extends all the way up to the nth dimension, where the sum of x integers to the nth power is an n plus 1 degree polynomial. But figuring out the coefficients of the polynomial for high powers is difficult, but thankfully there is a formula called Faulhaber's formula, where p is the power we are summing and n is the amount of them. The section that looks like a fraction but without the line is called the binomial coefficient, and the b subscript or is the Bernoulli numbers, which is a sequence of specific numbers which seem really random but show up in all sorts of places. If you want to try see the Bernoulli numbers or the integer power sum formulas, you can check out the program shown here, which I made, linked in the description. Thank you for watching. I hope you enjoyed the video. If so, please like and subscribe. Have a nice day. Bye.